Hey, what's going on everybody? Back again with another example of mesh current analysis, and in this case we have a circuit with two power sources and three loops. And yeah, we just want to basically go through and find out what all of the different currents are in each resistor or each branch, and we're going to do that using mesh analysis. So the first thing that you want to do with mesh analysis is identify on your meshes, which are your mesh currents. So we have I1, I2, and I3. What I like to do, which not everyone does, is I just like to identify on what the branch currents are as well. So I'm just going to label on the branch current through each resistor. And when I do this, I'm just going to assume directions. It doesn't matter which way you draw them. For example, IE up here, we know it's going to go this way, so draw it the correct way because this independent current source forces the current there. But for the rest, you can guess, but for example, like this one, you don't know which way this one's actually going to go yet until we do the problem. So just put them on in any way possible. When you do that, though, it is going to basically assume polarities based on the way that you've drawn it. So they'll be like this, like that, and like that. And that's going to be important when we do KVL in basically step 2 of mesh analysis. Before we move on, let's just throw on all of these down the side. And let's put them in terms of each other, or we'll put the green ones in terms of the blue ones, basically. So putting the branch currents in terms of the mesh currents. Now we know that the current here, IE, has to be equal to 2 amps because of the independent power source. So let's actually label that one on first. So no matter what, that has to be equal to 2 amps. And when we look here, we're saying I3 is like it's going around this way, around this loop. And so as it passes through this resistor, it's going to the right, but we know the actual current's going to the left. So IE is just equal to negative I3. Or I3 is equal to negative IE. Basically, I3 is equal to negative 2 amps. It's equal to 2 amps, but it's going the other way. Again, here we're saying that I3 is negative 2 amps, like this. And so negative 2 amps down is the same as 2 amps up. It's just basic vector addition. Okay, and let's just fill in the rest. For example, when we look at IA, we're saying that the mesh current is going to pass through from left to right through this resistor, and so IA is equal to I1. Let's put that in here as well. The same thing for IC. IC is just going to be equal to I2. And when we look at, for example, IB, we're saying that we have I1 going down and we have I2 going up. So if this is the net direction of I2, it's going to be equal to I1 minus I2. So we can just put that in for IB, so it's I1 minus I2. And we have a very similar logic here for the 2 ohm resistor. We have I2 coming down, and we have I3 going up through that resistor, and ID is the net direction downwards. So ID is equal to I2 minus I3. So when we're looking at this, we've got basically 2 unknowns. We're looking for the mesh currents. We don't know what I1 is and we don't know what I2 is, and we're going to have to figure them out. So what we want to do now is we want to do KVL for all of the loops in order to find out the unknowns. So we have to do KVL for loop 1 and loop 2. We don't have to do it for loop 3 because we already know what I3 is. So let's get started with loop 1. We have KVL loop 1. And here we can pick any random point. Let's start down here, and we're basically going to go the full way around the circle and come back here. So when we enter in through the negative terminal of an element, we're going to assign that a negative. When we enter through the positive terminal, like these ones, we're going to assign that with a positive value, and we're going to sum them all up to 0 to get back to the same voltage that we started at. And I'll just drop a little reminder here that V is equal to IR, and so what we're doing is we're summing the voltage drop, so the voltage changes. And for the resistors here, we don't actually know what they are, but we can find them in terms of their resistance times their current. So anyways, starting here at the red dot, we're going to enter through the negative terminal of our 3-volt battery. So we're going to start with a negative 3. And then when we enter through the positive terminal of this resistor, we'll assign a plus, and we're going to have 2 ohms times the current, which is IA. Then when we come and enter through the positive terminal of this resistor, we use a positive value here, and it is going to be 3 ohms times the current, which is IB. And that is all equal to 0. And what this is saying is we sum all of the voltage changes across each of these elements and we get back to the same voltage that we started with when we complete the loop. So now what we want to do is substitute all of these ones with a letter subscript for the mesh current. Again, some people jump straight to this, but I find it easy to make mistakes, and it's more like explicit if you do it this way, but if you're not taught to do it this way, then that's fine. Just jump straight down to this line and ignore the line above if you don't want to do it. So anyways, we're going to have -3 plus 2 times IA, but IA is equal to I1. So we're going to substitute that for I1, plus 3 times IB, and IB was I1 minus I2. So we have I1 minus I2, that's all equal to 0. And then we can just simplify this a little bit. Okay, so let's also do KVL for loop 2 now. And let's also just identify a point where we're going to start. How about right here in the top left corner? And again, we're just going to start here, and we're going to go the whole way around the loop, taking the voltage changes, and we're going to get back to this, like the same value. So it's all going to sum to 0. So when we first enter in this one, we're looking at a positive value, and we're going to basically have 4 ohms times IC. And then when we come around, we're going to enter in the positive terminal of this one. So we have plus 2 ohms times ID, and then we're going to come around and enter in the negative terminal of this guy. So we have minus 3 IB, and we set that all equal to 0. Okay, so now what we want to do is we want to substitute in basically the letter subscripts for our number subscripts or for our mesh currents. So for IC, well, IC is just equal to I2. So we have 4I2 plus 2ID, and ID is equal to I2 minus I3. So that's I2 minus I3 minus 3 times IB, which was I1 minus I2. And that's all equal to 0. And basically, I'll just fast forward, but we can simplify this all down into an expression for I1. And we're just going to take that whole expression and we're just going to plug it back in right here to I1. And then we can also just simplify this down to get I2 is equal to negative 0.305 amps. And then we're going to take that and we're going to plug this one back into this expression where the I2 is, and we'll find that I1 is equal to 0.418 amps. So if you were just asked to find the mesh currents, these are the answers. I1 basically means we have the direction correct because it's a positive value, whereas this one we have a negative. So we basically, the magnitude is 0.305 amps, but the real sense of it is going counterclockwise, and same with this one. But if you're not asked to find the mesh currents and you're actually asked to find the branch currents instead, then we still need to do that one last step of plugging them back in and finding something sensible for these actual values. But it's pretty easy because we have the substitutions here and we can just figure them out pretty rapidly. So IA is equal to I1, which is just equal to 0.418 amps. So that means that we have the direction here assumed correctly, so it is going to be going to the right. Taking a look here at IC, IC is equal to I2, and I2 is equal to negative 0.305 amps. So we can write that down either as negative going to the right, or we can indicate that it is actually going to the left. However you prefer to write that depends on like if you're drawing on the diagram for your final answer or if you're putting it off to the side like this. But basically this is going to be equal to 0.305 amps to the left. Let's do IE as well. IE was the easy one. We already have it. It's 2 amps and we have drawn it to the left. So let's just put it here in purple as well, or pink, whatever this is, to the left. And then when we look at I1 minus I2, I1 minus I2, so 0.418 minus negative 0.305, that's going to give us a total value of positive 0.723. And that positive indicates that we have this direction correct, so it is going down. And then same thing here. We have I2 minus I3, so negative 0.305 minus 2. We're basically just adding 2 to that, and we're going to find that's a positive value of 1.69 amps, and that positive value indicates that we've got this direction correct, and that this is in fact going down. So that's honestly why I like writing these out from the beginning. and starting the first line here with them, because at the end, if this is your goal to write out these branch currents, then by already having them and already having the relationship to the mesh currents, at the very end you can just like bam 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 slam them out, and then you're basically done with the problem if that's what it's asking for. So yeah guys, hopefully that's clear, hopefully that example helps, and I will see you in the next video where we'll go over SuperMesh, which is a slightly modified version of this which we have to use in case there is a current source in between two meshes.